Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Last time we were talking about gravitational waves and their discovery. When they were discovered back in 2016, and as a culmination of over 40 to 50 years of work with the LIGO observatories being built, and the people who devised it and supported it through the decades got the Nobel Prize for for the initial discoveries. Well, since the initial discovery in September of 2016, there have been a grand total of six other, as of this particular time, six other gravitational wave sightings that have occurred, and we're going to talk about the most recent of those, the last one that was discovered, and it's the most important. So again, we're looking at the gravitational wave spectrum, and the spectrum here shows that gravitational waves themselves are predicted by general relativity, and the ones that are currently doable are with the terrestrial interferometers, which would arise from very rotating neutron stars that have little lumps on them, and they would make what's called star quakes. And also supernovae should be things that they see. Also, they should be able to see compact binaries such as combining black holes, which is the dominant number. The first five were medium-sized black holes, meaning a few tens of solar masses as they combined. But what if two neutron stars collided? Neutron stars, of course, are very massive objects that have been compressed to extremely small sizes. Most neutron stars are between, say, 1 and 3 times the mass of the Sun, and that whole amount of mass has been compressed down to something a few miles or a few kilometers in diameter. They're very, very, very tiny objects. They're extraordinarily dense. And in my neutron stars video, I discussed exactly the interior structure of these neutron stars and how incredibly weird it is. But basically, there's zero space between the individual nuclei in the neutron star, and you can come up with these wild phases of matter where there are no individual nuclei, where all of a sudden the interior of a neutron star is effectively one big atomic nucleus. Importantly, neutron stars can have a property of being a pulsar. One of the important properties is as they shrink, the magnetic field of the star itself gets more intense because the material isn't going away, and the material that makes the magnetic field isn't going away. So since it's not going away, as the object shrinks, the intensity of the magnetic field increases radically. It increases so much that the magnetic field itself can accelerate particles to nearly the speed of light, and as they get ejected out the poles, and it also creates hot spots on the magnetic poles of a neutron star. And if the magnetic poles are not aligned with the spin axis, then you can have what's called a pulsar. And the beams of light that come out from a neutron star along its polar magnetic field axis, because as electrons go spiral in the magnetic field at nearly the speed of light, they emit synchrotron radiation in radio as well as X-ray light, and we see these as X-ray or gamma ray pulsars. So a pulsar is an incredibly important element of the neutron star experience. And as pulsars spin down or get slower and slower, they fade away. So we should expect to see a large number of neutron stars throughout our Milky Way. And their effects are very important, as we'll see soon. Back in 1974, Russell Allen Hulse and Joseph Hulse-Taylor discovered a binary pulsar. Two neutron stars orbiting each other, both of them pulsars. And their discovery earned them the Nobel Prize in Physics in 1993. For a reason we'll discuss, and that's subject of this video, and the same thing in just a second. It's called the Hulse and Taylor pulsar binary. And each of these neutron stars, the initial neutron star was found to be rotating 17 times a second on its axis, and they eventually did, with follow-up observations, were able to determine that it was a binary neutron star. And they used the Arecibo Observatory that you see here, which is located in Puerto Rico. What they did that got them the Nobel Prize, though, is that since they discovered it was a pulsar, a binary pulsar, they timed the radio pulses for a long time and noticed that there was this incredible systematic variation in the arrival time of the pulses. They changed in a very smooth and repetitive manner, and their normal period is about 7 3/4 hours. And this variation was happening if their variations in this binary, the initial binary the initial pulsar they found, had a variation that changed smoothly, and that's if it was in an orbit around another pulsar. And that's the only way they found that. So he said, oh, this thing is changing. So if it's doing that, it's just in the same way that we would find a binary star. So we might find a spectroscopic binary. And instead of finding a spectroscopic binary, we found a pulsar binary. So what they discovered by looking at the variations between them is that the pulsar they orbit each other at about 3 light seconds, with a diameter of about 3 light seconds. And that's about 2/3 the diameter of the sun. So remember, 100 Earths fit across the sun. So this would be about 60 or 70 or 60 or so Earth diameters between these two pulsars. And each of the pulsars is about the size of a big island, such as Manhattan Island or so. So they can see each other in the sky in a certain way. They'd be very, very, very bright in X-rays. And they were able to determine that the masses of each of these pulsars was about 1 and 1.4 times the mass of the sun. What they then showed was that the pulsars' orbit around each other was gradually contracting. And as they showed that it was gradually contracting, that meant the period of the pulsars were shifting. And as they shifted, the periodic shift accumulated and accumulated. So what they found is that the pulsar timing, when they got the actual pulses from it, was getting closer and closer and closer together. And that's as a result of the two pulsars approaching each other. So why do they approach each other? Because they emit gravitational waves. So this graph is showing you the cumulative period shift of the orbit of the two pulsars as a function of time. And it takes years to watch it. And each of those red dots is a data point. The blue line that fits them is the prediction of general relativity if they're emitting gravitational waves. And that's how they're losing energy such that they're coming together. And notice how the prediction of gravitational wave emission exactly matches the dots of the data. So that's what earned them the Nobel Prize in 1993, was the implicit discovery that gravitational waves were being emitted by this pair of neutron stars. Well, they're very far apart, 60 Earth diameters apart, so it's going to take them 1 billion or so years in order for them to fall together. And so we won't see them collide or anything, but it just shows that there are two pulsars that can be in very close proximity to each other, less than the diameter of the sun, and that they are apparently emitting, or at least they are emitting gravitational waves, but no gravitational wave detector had been built yet in 1974, nor had one been built by the time that they earned the Nobel Prize. It just showed that gravitational waves were the best explanation for the change in the period of the orbit of these two binaries, these two pulsars. Okay, so with that in mind, people were saying, wow, this is really great. There must be lots more of these things. So what happens when these two things collide? So there was a huge number of studies of pulsars. It's an active area of research of neutron stars and pulsars. And this radio telescope, which is the Lovell Telescope at Jodrell Bank Observatory, which is in Cheshire in northwest England, it was in 1957 when they first built it. It was the largest steerable radio telescope in the world at 250 feet in diameter. Now, Arecibo is not steerable. This is an enormous, enormous thing that's is 76 meters in diameter. So it's almost the width of a football field, an American football field. Now, the Green Bank Observatory in West Virginia is a bigger steerable scope, as well as the Effelsberg scope in Germany. But this is a big one. So this is a huge, huge, huge telescope. And it's one of the Pulsar workhorses in the world. It's discovered a number of binary pulsars, as well as discovering 100 pulsars on its own. And in September of 2006, they were able to assist in showing a different double pulsar, not the Hulse-Taylor pulsar, but a different double pulsar was also emitting gravitational waves. So the action of discovery of pulsars is a major part of radio astronomy. So what's a double pulsar look like? So one of the first known double pulsars opens up like this. Well, the Hulse-Taylor binary, one's a pulsar and the other must be a neutron star, but we can't see it. But this is a double pulsar, and they orbit these two double pulsars. Orbit, and this is a double pulsar. The other one would be a double neutron star with only one pulsar being seen. That's the Hulse-Taylor binary. But this is a double pulsar seen by that telescope. So these two pulsars orbit around each other. That was discovered by the Lovell Observatory. And orbit around each other in about 2.5 hours. One of the faster pulsars spins 45 times a second, and the other spins 22 times a second. And as they orbit each other, they found that they too would be emitting gravitational waves in terms of how they're falling together or getting closer and closer. Now, each of these neutron stars, have much larger masses than our sun. And these are incredibly large things and very, very, very close together. So how might a double pulsar be formed? So let's look at this, how they might be formed. In the upper left-hand corner, we see a supermassive star exploding in a Type II supernova. It becomes a neutron star with pulsar activity. Its companion in a close binary is also a massive star, goes through its evolution, and then while it's about to die, it's dumping stuff onto the companion to spin up the other pulsar into a millisecond pulsar. Then it explodes, forming a neutron star, and which is also a pulsar. So the upper left-hand corner shows the evolution over, say, 10 or so million or 20 million years to get those stars from main sequence all the way through red giant phase. And as the second red giant swells up to fill its Roche lobe, it'll dump material through gravitation, because the gravitational balance point dumps things across to the other neutron star. Then they explode, and now you've got a double pulsar. So the right-hand side image shows our current observation of a double pulsar, where we see the beams coming towards us as these two stars rotate on their axes. Their magnetic fields are not coincident with their rotation axis, so we occasionally see these flashes of light from them. And as they orbit each other, they slowly lose energy in gravitational waves until they get close enough to collide, like we see in the lower left. Eventually, this double pulsar will get closer and closer and closer. As they orbit closer together, they will eventually collide in a titanic collision. As we see in the lower left, they'll form either a hypermassive neutron star for just a fraction of a second, and then they will form a gamma ray burst, which is the light that you saw there in these jet-like structures. So the end result of one of these things is either a supermassive or hypermassive neutron star, which will only live for a few seconds before collapsing down into a black hole. So this is what we would call a kilonova. And the lower left-hand image shows what a kilonova looks like, which is a much more power, about 1,000 times more energy than a standard supernova. That's why it's called a kilonova. And these things are also the sources for gamma ray bursts. So we can expect that some gamma ray bursts that we talked about in the previous lecture on gamma ray bursts should be due to colliding neutron stars. And on August 17th of 2017, a gamma ray burst was detected by both the Fermi and Integral Gamma Ray Observatories in orbit. And just a few seconds prior to their detection, the LIGO Virgo Association, because now the Virgo Gravitational Wave Observatory was online in Europe. So now they had 3 observatories, unlike the others. The first initial discovery, which is simply by LIGO Hanford and Washington and Louisiana. This is 3 observatories able to confirm all at the same time. And notice the gamma ray bursts occur just a few seconds, less than 2 seconds after the arrival of the last moments of the gravitational waves. So this was the first ever joint observation of a gravitational wave and some form of light. So the Fermi Space Telescope and the Integral Space Telescope both have triggering mechanisms that send information to observatories and observers around the world to go try to figure out what's going on and observe these things in, say, X-ray, optical, infrared, radio, what have you, as fast as you can, if you can. So they send out to massive observatories. Now the Virgo team had a glitch in Hanford that caused them to be delayed by 27 minutes after their initial detection, but they were able to clean it up and say, oh, the glitch made it difficult to find, but they actually looked at it and said there's a signal inside there, and it was a massive, massive, massive signal that they were able to find, and this began the process of a worldwide effort to observe this event somewhere in the electromagnetic spectrum. This was the thing that was being hunted for, the light or electromagnetic counterpart to a gravitational wave event. So this is one of the landmark days in all of astronomy history, was August 17th, 2017. And that signal looked a lot like this. And so what we see is the gravitational wave signal according to frequency, and so they have all the static, but then there's a signal that goes through the frequencies as a function of time left to right, and the actual event was at time 0 that you see there, but stringing all the way back, this looks like it started about 2 minutes prior when the signal actually could be detected. However, the triggering only happened about 30 seconds prior to it. And the summation of that trigger went out to everyone in the world 27 minutes later because there was a slight glitch at one of the observatories. What's funny is that they compare this signal to say, what is the chance that all that random static that you see in there could actually have just kind of organized itself or randomly positioned itself to make this shape? And they make enormous numbers of statistical studies to determine whether or not this thing is actually is a false positive, meaning that's just static, or whether or not it's a real signal. And so they create a false alarm rate characteristic, and they said that this was the only chance is that one in a trillion was the capacity for it to be a false detection. So they didn't think that for 1 in a trillion, that's over time, and that means that they would say this would only happen once in 80,000 years of observing. If they observed with the observatory for 80,000 years, only once would this happen randomly. So they said, well, this is a real signal, and they then scanned their data. They found the signal lasted 30 seconds. All of the other gravitational wave events that occurred last only fractions of a second. So this was incredibly different than all the other signals combined, and because it lasted a lot longer, that means it was much less massive. Because more massive things, they change more quickly as they're about to collide. So they were much less massive. The only thing I could think is that they'd caught their first gravitational wave from neutron stars. Since all the other things were more massive and much more quick, just like the first one I showed you, it only lasted a quarter of a second from rising out of the noise into the final chirp at the end. Note that the frequency shows low frequency at the bottom and high frequency at the top. So literally all this would sound like is whoop. That's what it sounds like. It's like a whoop. And this was a merging neutron star because of how long it took and basically the signal itself. All right, so how do they actually know where to go and look for it? So then the race was on to find this thing. So the Fermi Space Telescope could see in an oval, Integral could see in a band, and then LIGO and the two LIGO observatories and the Virgo observatory could see in a banana type shape to hunt it down. And so all those circles that we saw before, those are the possibilities of where it could have been in the sky. So you saw that there's a very small number of objects that it could have been. And they were able to isolate the location in the sky because the Virgo detector in Europe didn't detect anything. Remember, the observatories from the previous lecture showed that you had to actually get a signal by having the gravitational waves pass perpendicular through the detector. The fact that it didn't get signal at all in Virgo meant that the gravitational wave signal did not go at any angle perpendicular. It went flat to the observatory rather than perpendicular in any level. So since it went flat, they were able to reduce the entire field of view to about 30 square degrees, or about 60 times the size of the full moon. And that launched a search, a massive search, and within 12 hours, this galaxy had been seen to have some sort of event happening in it. And this galaxy is NGC 4993. And NGC 4993 is an elliptical galaxy about 130 million light years away. And on the left-hand side is a Hubble Space Telescope image from April 28 of 2017. And on the right is from the SWOPE supernova survey from Santa Cruz, where there's a new bright dot right in there. And this was taken by that observatory at that date within 6 hours of it. And when they saw it, they said, there it is. This was the first optical image of this observatory, of a gravitational wave event. Now, that's not gravitational waves we're seeing. We're seeing optical light, visible light that came from something that captured gravitational waves. One of only a handful of galaxies inside the search area for this object. So the SWOPE team was able to compare against other previous Hubble Space Telescope images, and that's when they knew they got it. So what's funny is that apparently the people at Santa Cruz, when they said, it didn't really elicit this huge reaction. Hey, there's something new. I was like, oh, there's a dot there that wasn't there before. Interesting. Because they're hunting for supernovas. And a kilonova is just like that. It's just another little bright dot right next to the galaxy. So what happened was, this was the first detection in visible light, not invisible light, but with optical light of an event, of an object that did this. And this is bright enough that if you had a half-meter class telescope or a 1-meter class telescope, you could easily image this galaxy. In fact, some observatories, such as iTelescope, which is a per-pay amateur class observatory, but it also can be used for research, the larger instruments there could easily have observed this event. So the first light with Hubble Space Telescope, Hubble swung around, and they swung the Hubble Space Telescope around to take a look, and yes, they saw it fading away. Other observatories had seen it within 12 hours. Hubble Space Telescope watched the flare die over the course of 6 days. They looked at it about the 20th or so, 22nd or so, and started watching it over the course of 6 days. They had other things to do, and they couldn't exactly rip it away. But they got the Hubble Space Telescope as soon as they could to see this kilonova event and watch the fading glow of this object. It was also observed in infrared. This is the Spitzer Space Telescope run by NASA, JPL, Caltech. And the Spitzer Space Telescope also saw the event. They were able to, they were looking specifically in the channels of 3.6 and 4.5 microns, which is much longer than visible light. It's deep in the red, and so they were able to see it in infrared. Also, the Chandra X-ray Observatory, the circles show where it is. In previous on the night, there were also in the previous section, the gravitational wave event itself only showed up later. And so there was a counterpart that occurred a little bit later, not immediately, in X-rays. And furthermore, the Very Large Array in New Mexico, the VLA was swung over there by Greg Hallinan and Kunal Mooney. They got the little arrow points out the object. The center is the supermassive black hole, the center of that galaxy. But this is the VLA radio image, and that radio image comes from the interaction of the material in the surrounding medium around it. So this is also part of their work. And so when they were this was part of a high-speed alert that they actually working with too. And the Australia Telescope Compact Array, or ATCA, also detected it on September 5. So VLA and radio observations occurred too. And here we can see a little summary plot of it with a Hubble Space Telescope image. We can see the Swift Ultraviolet Observatory taking ultraviolet pictures of it. Gemini South is, instead of Spitzer now, looking in the infrared, and the VLA in the right. So this was observed by many, many, many groups. So what did this look like if you happen to have been close up? A merging pair of neutron stars. First, it would take about, their merge took about 2 minutes, but the last merge of it took fractions of a second. And there it was, they merged together, and as they exploded, they emitted the gravitational waves, and a huge burst of gamma rays came out, and material flowed out from them in the cosmos. The gamma ray bursted material then intersected with the interstellar medium to form the gamma ray burst that we've seen in other objects. This particular thing was, as they plowed through together, the amount of material that was turned into mass was about less than a quarter of a solar mass. And so we see that when neutron stars make the collisions, we're just summarizing it here. The upper right-hand corner shows the collision of the two neutron stars, and as they collide, they form gravitational waves, which are kind of the shimmering, ghostly rings that you see coming out. Those are the gravitational waves. They come directly from the interaction, the collision of them. So it probes general relativity in the very, very, very strong region of where things are going crazy in gravity. But then the light comes later, in a couple seconds later, as those jets are formed, and then we see the jet on the upper right hand and the lower right, and that as the material slams into the interstellar medium around it, that shocking of the material heats the material such that it glows in gamma rays, and that's the source of the gamma ray light. And we talked about that in gamma ray bursts in the gamma ray burst lecture, as we see in the upper left hand image that comes from that lecture. But most interestingly enough is the lower right image, is all the debris that came out from this collision, because it probably formed a black hole, but not all of it went into the black hole. The total amount of material that went into becoming the black hole was between the two was kind of minimal. So the merging of it converted about a quarter of a solar mass into gravitational waves, and but the important thing is that material that came out that didn't fall into the black hole created huge amounts of heavy atomic nuclei. In fact, it was estimated and then subsequently seen in the spectrum of this kilonova, because so many telescopes and observatories could actually take a spectrum of this light from a distance of only 130 million light years, that it was determined that approximately 16,000 times the mass of the Earth in heavy elements was formed, which is wild. And approximately 10 Earth masses of gold and platinum were formed at that time. So just think like 10 Earths of gold and platinum were made in that moment of collision. So this is very interesting, because this has been shown in terms of the follow-up by the Chandra X-ray Observatory, because heavy elements like these will emit X-rays, or at least the products that would radioactively decay to them will emit X-rays, because they're coming off in that explosion. That kilonova event strongly excites the nuclei, as well as creates radioactive elements that would then decay to these heavy nuclei, such as gold and platinum. So there's a lot of X-rays that come, in this spectrum on X-rays determines what the material is. So that's how we know that that there was a huge amount of gold and platinum that was made there. In fact, this provides direct observational support for an incredibly important element of the Big Bang. The Big Bang produced the hydrogen and helium of the cosmos. Stars such as the massive stars like Betelgeuse and Arcturus, supermassive type 1 supernovae, such that would have formed the pulsars in the first place, those would give us like oxygen and aluminum and phosphorus and argon and iron and nickel and cobalt and all other things like that, up to krypton or so. But those things would create and push out the iron. But the very heaviest elements were not, the mechanism that was understood to be creating them would not have been an exploding white dwarf, would not have been an exploding supermassive star, wouldn't even be, it would have to be the destruction of neutron stars. So if you have two neutron stars merging, they seem to be creating most of the heavy elements, and that's the color yellow in this particular periodic table set that we're looking at. They would be creating most of the heavy elements, including all of the iodine, all of the platinum, and nearly all of the gold in the entire universe. So all of the gold that you've ever encountered was created inside of as a result of two colliding neutron stars, and this is observational evidence for that. This is the first observational evidence for it. It was theorized up until this point, but now we know that it's actually occurring. That's just an amazing, amazing thing. And that was discovered by the event that happened on August 17th of 2017. The first observation of two neutron stars colliding, both in gravitational waves as well as in electromagnetic spectrum, all across the spectrum. One of the most studied transient phenomena in the history of astronomy happened in that day. Well, what this means is that there's a lot more to see of all of the gravitational wave events. And so here's a little slide that shows the ones that have been seen. You can see there's 5 events that have been seen by the LIGO-Virgo collaboration, and there's 5 black hole mergers where the 2 black holes collide. Now they don't make heavy elements. Why? Because black holes are already inside their event horizon, so nothing gets out. So the black holes simply collide. They don't make a hypernova type explosion. They don't make a kilonova type explosion. They just make a gravitational wave event. However, neutron stars make a lot of light because their physical structures are still objects of extreme density, so to rip them apart and will create a huge amount of debris and a gamma ray burst. So now that we know that gamma ray bursts come from 2 neutron stars colliding. We do know that. We also know they come from hypermassive stars collapsing. But this was the most studied, as we can see, of all the neutron stars that have been seen by LIGO and Virgo. The LIGO-Virgo combination actually showed the first one ever. And hopefully there will be many more to come as they've taken the system offline to do some upgrades, and because it's a huge undertaking actually to do this. And so only 6 have been found so far as of the fall of 2018. And hopefully there will be more in the future, because this is the future of astronomy, is gravitational wave observing, which involves enormous collaborations, extraordinary commitment, and then commitment between particle physicists, engineers on the ground, and astronomers looking with multiple different kinds of telescopes. So this incredible thing can then be summarized. They have a cool little fact sheet. I'll kind of zip through it because this is really neat. All sorts of stuff. There's some factoidal things. And finally, there's some websites for you to go take a look at because, heck, that's what they're all about. The LIGO Observatory, as well as the Virgo Observatory, and this is one of the most important things that happened in 21st century physics. Thanks again, and we'll see you soon.